All right, we'll get started, and happy Friday, everybody.
Yay.
So hope your first week of the spring quarter is going well. Today I'm going to take attendance using the online polling tool. Okay, if you've never done this before, you're going to go use your phone or your computer or whatever it is. You're going to go to onlinepoll.ucla.edu. Okay, so you'll need some kind of web-connected device. So either your phone or your computer. This will get you there. onlinepoll.ucla.edu. You are going to log in using your UCLA ID, and then and once you're there, you should see a poll that says 102C, April 6th, 9:04 a.m. here, okay? So, and then we'll say today, choose response A. All right, so response A to let us know that you are present. So, online poll. And so this is how we will take attendance. And then for today, choose A, okay? Now this is important. Don't text your classmates who are not present and tell them to respond to the poll, okay? The poll here is a way for me to take attendance, and it's for you guys who are here to respond and let me know that you are here. Are you guys able to see the poll and respond? It looks like, okay, we are getting responses, so that's good. This became an issue last quarter. You know, I took attendance one day and I got a bunch of responses, but looking out at the classroom, I could tell that the number was not quite right. And so I went down the list and I called everyone's name, and we found a bunch of people were not here. And so I think I updated my syllabus to reflect this, but if a student is caught responding to the online poll but is not physically present in the classroom when I do that roll call, you know, that student's going to lose their entire portion of the attendance grade. Okay, so I'm not going to do it every time, but that threat is always going to be, you know, a little bit present in order to try to keep everybody honest. So you know, please don't abuse the system. It's based on trust here, right? Students have told me that other systems exist that use like GPS to make sure that you are physically present in the classroom, okay? And they do exist, and I've checked those out, but I have not found an option that's free, okay? These companies, they're for-profit companies, and they charge, you know, $25 per quarter for the students just to have this app that does the exact same thing that this tool does. This tool is offered by UCLA and is free, but it doesn't have GPS tracking. I don't want to make you guys pay money. I would get nothing out of it, and all of your money would just go to some company that I have no interest in, and I don't want to do that, right? I want to be able to trust you guys, to be honest, not have to use GPS tracking, not, you know. I want this to be a good way for you to, you know, for us to be able to take attendance without students, you know, trying to game the system here. Okay. All right. Is that good? All right. You guys are. I'll leave that open for the next I don't know, however long necessary. And what happened here? Oh, wait. Okay, I don't. All right. Okay, so we'll have that. That's there. And where are my notes for today? Here they are. Okay, and we'll get started. So go ahead, yeah, respond to the poll, online poll, choose option A. Again, please don't tell your friends and try to get, please don't game the system. This is based on trust. If I can no longer trust you guys, then that will break my heart, okay? Okay, so we've covered, if you haven't noticed, homework 1 is posted online, okay? So homework 1 is up, and that will be due next Friday, so a week from today, 6 p.m. And it covers inverse CDF method, and then it will also cover rejection sampling, which we will cover today and also on Monday, okay? And there's also this silly exercise where you're gonna estimate pi by throwing random dots at a square, okay? And I hope it's a good exercise. I mean, at least it covers the stuff we've done in class. Okay, so far we've covered the inverse CDF method, okay? So, oh wait, hang on. Before I get into today, rejection sampling, part of the homework, or actually most of the homework problems are generate values from some random distribution. It'll say like generate values from the exponential distribution, or generate random values from the normal distribution, or something like that. And in order to kind of see if your random number generator is working, I have you guys run what's known as the Kolmogorov-Smirnov test, okay? So we just call this the KS test, but it's the Kolmogorov. I'm sure I'm pronouncing this terrible, just the way an American would pronounce it, okay? So we have that, and this is, there's lots of tests, but this is one, this is a nonparametric test to see if a sample, it could be either two samples come from the same distribution, or a sample comes from some defined distribution, okay? Comes from a distribution, or if two samples come from the same distribution. And I think I linked to a little short YouTube video kind of covering the KS test in a little bit more detail. And basically the idea here is, the big idea, and I'm going to avoid the math, but the big idea is you compare the empirical CDF to the empirical CDF function to the theoretic CDF. Or if it's a two-sample, or to another empirical CDF. Okay, and the way the empirical CDF works is that if you have, say, 5 data points, so this is just a very simple example, okay? If you have 5 data points, and the data points are 1, 2, 4, 6, 8, okay? Then the empirical CDF will basically look like this. It's for x less than 1, the ECDF is 0. Okay, and then because we have 5, everything will increment by what? 0.2, okay? So basically for x between 1 and 2, the ECDF is 0.2, and then for x between 2 and 4, the ECDF is 0.4, et cetera, until you get to x is greater than 8, and at 8, the ECDF is 1.0. Does that make sense? I guess it's not. Okay, 4 and 6. I have to fit 2 more numbers in here, okay? And basically you would just plot this, and then you'd say you got 1, 2, 3, 4, 5, 6, 7, 8, and your ECDF would look like, it's a line down here, and then at 1 it goes up, and then at 2 it jumps up again, and then at 4 it jumps up, and then at 6 it jumps up, and then finally at 8 this is the maximum of there, okay? 1, 2, 3, 4, 5, yep. Okay, and that's the ECDF function, okay? And you would compare this to some empirical distribution, okay? So maybe, not empirical, some theoretic distribution. And this could be, you know, x comes from uniform maybe 0 to 10 or something like that. And if that's the case, then the empirical distribution, the empirical CDF would look like this. It would start at 0, and then at 10 it reaches 1. Okay, so this is what the theoretic distribution looks like. Is this okay? All right, so we would expect even everything to increment continuously between the values 0 and 10. And then the KS test basically measures the difference between the empirical value and the theoretic CDF. Okay, the empirical CDF and the theoretic CDF, and it finds the maximum value, and it has a way to calculate significance based on that difference. Okay, if the difference between the empirical and the theoretic is very large, then that would be an indication that your observed distribution is different from the theoretic distribution. Okay, if the difference between those are very small, then it would be an indication that it doesn't prove that they are from the same distribution, but it would not be a warning sign. Okay, so the KS test cannot prove that some sample comes from a distribution, just like that's a hypothesis test like everything else, right? So you start off with the null assumption that a sample does come from the distribution, and you go through the test, and you might find it does not conflict, and you would just say we have no evidence to say that our sample does not come from this distribution. Okay, and that's all. That's the best you can say. You can never say that for sure this sample comes from this distribution. That's just not going to be possible. But you can say we don't have evidence to say otherwise, and that's all you can hope for. So effectively, you're hoping for a test statistic or a p-value that is large. Okay, a large p-value that would give you an indication that we have no reason to doubt that our distribution comes from some that our sample comes from some specified distribution. Okay, can I resize this so you guys can see? Okay, so let me just do a very brief demo here. Okay, so let's clear this plot. Okay, so here is S is going to be a sequence from 0 to 1. So here I'm going to just have the random uniform from 0 to 1, and the uniform CDF is that, and I can plot this. I can do plot S versus uniform underscore CDF, type equals L, and that's the uniform CDF. I suppose I could go from negative to higher, but that's the uniform CDF. No big surprise there. Okay, so if our only data set, we only have one data point at 0.2, then the empirical CDF looks, wait, that's not right. Oh, I was wondering what was going on. Okay, so the empirical CDF here starts at 0, and then at 0.2, we're at 100%, right? It's kind of just like what proportion of the data is at 0.2 or greater. 100% of the data. That would be the empirical CDF, and we can compare that versus the theoretic CDF, and we see there's a huge difference, but there's only one data point. Okay, if we have two data points, then our empirical CDF looks like this. It would consist of 0.2 and 0.5. Then at 0.2, we have seen 50% of the data, and then at 0.5, we've seen 100% of the data. Okay, 100% of the data is at 0.5 or less. So that's our empirical CDF, and again, we can compare that to the theoretic CDF. All right, here's a few more data points. So if I have 0.1, 0.2, 0.25, 0.3, stuff like this, we can see at each point our CDF increments, empirical one, and we compare this to our theoretic. If I take a random sample using our UNIF, this is the data that I get. I have 20 data points, and we would have to sort this, but the empirical CDF function does that for us, and it plots it accordingly. And this is what our empirical CDF looks like. At each value increments the CDF by 1/20th, 0.05, and we compare this to the theoretic, and we see basically this value is the one that deviates the most, or maybe that's this one that deviates the most from the empirical CDF. And the KS test basically does a test here. So one sample Kolmogorov-Smirnov test, and it gives us a p-value of 0.85. All right, so it's a very large p-value, and it says basically that we have no reason to doubt that our data comes from the uniform distribution. So right now we don't have any indication that it does. But let me say, what if I did Z is our norm from, let's say we're going to take 20 values from the normal with a mean equal to 0.5. Let's go ahead and see what Z looks like now, okay? And if I do this, ECDF of Z, just go ahead and do this. Let me get rid of the. Okay, this is what the empirical CDF looks like for the normal, and if we compare that to the theoretic CDF of random uniform, which really goes from 0 to 1 only, okay, and up here it's at 1 and down below it's 0, okay, we would get the impression that our sample of data does not come from this distribution, okay, and we would run the KS test, okay, comparing Z to p unif, okay? And here we get a very small p-value, indicating that it is quite unlikely that our data is coming. Well, it is quite unlikely that a random sample from our uniform distribution would produce values like this, okay? Now, obviously, if the KS test does not take into any account any kind of mathematical theory, it just measures kind of the difference between this and this. And if you said this was the empirical CDF and you know it goes from uniform 0 to 1, as soon as you see a negative value, you know that it can't be from that distribution, okay? The KS test doesn't know, and it doesn't really care. It has a way to calculate some stats for us, but it does give us a tiny p-value, which would indicate that we should reject the null hypothesis, and we have evidence to say that our sample of data does not come from the random uniform, okay? For a one-sample KS test, you give the arguments are your sample of data. In our case, my sample of data is z, and then the other argument is the CDF of the function. So in our case, we are doing the CDF for the uniform, so that's going to be p unif, okay? You can also alter things. You can say p unif from -2, you can say min equals -2. You can pass larger arguments. You can say min is -2 and max is equal to 2, okay? And it doesn't update the graph here. You'd have to update that yourself, but you can pass arguments to that, and you can see that our p-value gets a little bit larger. Whereas I can do a KS test, and we can compare it against the p norm. If I do p norm, it says it's quite unlikely, but that's because my values came from p norm with mean equal to 5. So if I wanted to have p norm mean equal to 5, or 0.5, then I can pass that argument as well. And when I do that, my p-value is quite large at 42%, thus indicating that we don't have any reason to doubt that z comes from p norm with mean equal to 0.5, which is exactly where our data came from. Okay. Does that make sense, the use of the KS test? All right, and so that's just one way for us to verify if a sample that we have is coming from some specified distribution. There are other tests we have for like normal data. You have the Shapiro-Wilk test and all these things that you can kind of read up on. Oh, okay, and let me talk about what we do for discrete distributions. Okay, so this is the KS test. Okay, did everybody get a chance to respond to the poll for attendance? Okay, and so I'll go ahead and I'll close the poll there. And I won't do a roll call today, but again, yes, in the future, please don't try to game the system there. Okay, and then for discrete distributions, you have lots of options, but I think a common choice is we can use the chi-squared test. Chi-squared goodness of fit test. What class is the chi-squared goodness of fit test covered in? It's not covered? Okay, well anyway, all right, so the okay, so the brief overview, okay, is that so with a discrete distribution, your data will come in as counts, right? You'll have a frequency table. So your data, your observed data, will basically be the value and its frequency. So maybe these are the values that you can get, and if it's binomial let's say, binomial with n equal to 4 and p equal to 0.5. What is this? Okay, so we'll do d binom 0 through 4, 4, 0.5. Okay, so 0.0625, 0.25, 0.375. Okay. So that's d binom, and it would look like this, right? 0, 1, 2, 3, 4. This is your PMF. So this is your, I'm sorry, this is not the observed data. This is the theoretic frequencies. Theoretic relative frequency. All right, and then so let's say you have, I don't know, 100 samples, okay? And your observed data, x, and then the observed count, 0, 1, 2, 3, 4. Maybe you get 0 5 times, 1 27 times, 2 40 times, 3 20 times, and I can't do the math. Okay, 60 plus 87 plus 5 is 92, so we would have 8 here, okay? So this is what we have, right? So this adds up to 100, okay? That's your observed counts. What you would expect, your expected count would basically be the probability that x equals 0 times big N, in our case 100. So we would expect 6.25, we would expect 25, we would expect 37.5, expect 25, and we would get 6.25. And your chi-squared statistic is found by doing the observed minus the expected squared over expected. And you would sum this up for all possibilities, okay? So basically you're just taking, you know, what is the difference between what you observed and what you expected. For each category. Okay, so that's going to be the difference between observed minus expected. And then to kind of make it follow a chi-square distribution, you square it, you divide it by what you expected, and you go through this process. Now you don't have to do this manually, you just tell R, do it, and it will do that. Basically in R you would use the argument chi-squared chi.sq test or chi-sq test or something. I forget. Okay, chi-squared test is a function in R. You pass it your vector of counts. You also pass it a vector of probabilities. You basically pass it this thing, and R figures out your expected count. It figures out your chi-squared statistic, and it will tell you if any of these differences matter. Okay, so we expected to see 20. The number 3 show up 20 times, and I'm sorry, we expected it to show up 25 times, and when we did our sample, it only showed up 20 times. Is this a problem? Okay, maybe, maybe not. Maybe this is within the realm of normal variation. The chi-squared test will figure this out for us. Okay, and so that's what it does. The null hypothesis is that these proportions are correct. And the alternative hypothesis is that the proportions for one of the categories is wrong. Okay. The thing is that all of your expected counts for the chi-squared test to work, there is a central limit theorem underlying it in the background. It's a little, because the chi-squared distribution is based on the z distribution. And basically, you need to have an expected count of 5 in at least all the categories. And so if you have you're doing the binomial distribution, some of your categories might have very low expected probabilities and thus very low expected counts, okay? And the chi-square distribution will fail in those cases. And so what you need to do is you need to collapse the categories. So for example, this is not a problem here, but if this number wasn't 6.25, but it was like 1.25, I would have to collapse that category into like an adjacent category. So I would say, so we would check for, how many times did we get 0, how many times did we get 1, how many times did we get 2, and then the last one we would say, how many times did we get 3 or 4? Okay, and we would just basically combine categories together until we get a reasonable sized contingent, okay? So, we might, so if you wanted to do something on like political parties or something, you would probably have a category for Democrats, a category for Republicans, and yeah, you could have like a category for no party affiliation, but then, there are a whole bunch of other like small political parties, right? Or smaller ones. There's, Libertarian and Greenpeace. Those are like the two larger ones of the smaller ones. But then there's like American Independent and all of these things. And you could like try to parse this out, but in like a smaller sample, you might have expected counts of only 1 or 2 for each of those categories. So in those cases, you'd have to just create kind of an other category that combines a bunch of these things into it. And so, it's unfortunate for the people in these, very small minority groups that they just get grouped up in other, but, that's how we have to do it. Otherwise, the math that calculates these statistics falls apart. So, so that's what we have to do, okay? Is that all right? Yes?
Okay, just got a question on chi-square. Is that
O is observed.
Observed and
E is expected, okay? Sorry, this was like, maybe it's not a safe assumption, okay? But like, maybe it's not covered in Stats 10, but it's probably covered in Stats 13, where you would cover the chi-square test. But I feel like you guys are stats majors and smart enough, and you can go on Wikipedia and read about the chi-square test and learn a little bit more on your own, right? Like I don't feel like I have to like hold your hand and walk you through all of these things.
It's in 101A.
101A.
I
Okay.
remember it was
All right. It should be.
at least.
It should be somewhere. Okay. And if not, you guys are all very capable of teaching yourself a little bit on your own. So. So here you go. This is the chi-square test. We can use it to test if the values you observe from a categorical or discrete distribution match what we are expecting for a categorical or discrete distribution. Okay, yes?
So for chi-square test, so denominator, did you purposely put expected value? Or?
Yeah, it has to be expected, okay? Because, so if you're expecting like 100 values for category A, and you observe 105, okay, that difference between 105 and 100, in the numerator you have a difference of 5, but 5 versus 100 is not that big, so that's why you put the expected value of 100 in the denominator to kind of normalize that. Whereas if you are expecting only 10, okay, and you observe 15, okay, 15 is 5 more than 10, so that numerator portion is going to be the same, but 15 is like 1.5 times what you expected there. So you do, 15 minus 10, so you have a deviation of 5. That goes 5 squared goes in the numerator, and you divide it by 10, and that's going to contribute a larger amount to kind of the total deviation that we've seen between what we expected and what we observed. Okay, so the expected is definitely in the denominator to kind of say larger categories, you can have a little bit more deviations. Categories with smaller expected counts, these deviations are problematic. Okay. All right, and so so that's that. In R, it runs basically something like this, and so you could have some vector. We could say y is some vector. So I could basically, what did I say? We observed 5, 27, 40, 20, and 8. 5, 27, 40, 20, and 8. Okay, and then we would have to pass it the our p's are going to be d binom here. So right. So y is my vector of counts. P is my vector of probabilities. Okay, and I would just do a chi-squared test between y and p. Oops, I have to do chi-squared approximation may be incorrect. Is that right? P equals P. Okay, you have to say P equals P. Okay, so this is chi-squared test for given probabilities, because that's what we're doing. Okay, and so in our case, we get a P value of 0.7235, and so if this is what I observed, if I flip the coin 4 times and I do this 100 different times and I get these counts for each thing, then this doesn't deviate very much. Okay. On the other hand, let's say I'm going to bump this up to 12 and drag this one down. What was it before? It's 5, so I'm going to add 7 to here, 12, and take away 7 from there. So this, I think y still adds up to 100, right? Okay, so here I've got, so this is what I have, and this is what we expected. And so here our p-value drops. It's still not significantly different, but it does say, you know, you are less likely to get this kind of data if these were the true given probabilities or things like that. Okay. All right. Is that okay? Yes. Question.
One more question. I just opened the Wikipedia. So the summation. So for the chi-square, it's like outside the fraction, but yours is on the denominator.
No. So order of operations says you do the summation after you do the multiplication and division. So. Is it like if I move this like that, it's the same thing, right? Because it's not some of the, you only have one you don't have one expectation for the entire thing. You have to like, okay, the Wikipedia page probably says it like this, right? It puts this in parentheses. But, you know, order of operations, you have to do the multiplication and the division before you can do the addition, right? So the summation is naturally going to happen at the end. So it's the same, I think. You know, it's not that I didn't have this. Okay, I didn't write that. That would be wrong. Okay. So, yes.
When we're looking at p-values, is our rejection number still 0.05, or do we just look at it and just go, it's small?
Yeah. Every alpha 0.05 is like something we do in Stats 10 because we don't want to give you hard rules. The truth is you should always just look at the p-value as kind of this flexible thing, and you say, well, it looks big, it looks small. My statistical judgment tells me this. Okay. We spent way too long on this stuff, and that I get. You know, that's fine. Maybe we're going to fill in some gaps that that existed from before, and that's okay. All right. Can I move on? Okay. All right. So we need to cover rejection sampling. Okay. And today, what we are going to do, we're going to just do the uniform case. And rejection sampling is basically, we use this when finding the inverse CDF is hard, okay? So, for example, CDF of the normal distribution is like doesn't exist in closed, does not exist in a closed form. Okay, because you got to integrate basically an e to the negative x squared, and that's like we don't have a closed form solution. See that? So what can we do? Here's a. I'm not going to do the normal distribution. We'll do that. Well, we'll see how far we get today. We'll have to do it on Monday or Wednesday of next week. Let's say you have some distribution. So we'll say x has PDF, f of x, and we'll just say this is sine of x, okay? And for we'll say for 0 is less than 0 less than x less than pi over 2. Okay. So in this case, what does our, this is like the first half of the sine function, right? 0 to pi over 2. And we want to get samples out of this. How do we do this? Well, one is we could do inverse CDF, and this is one that we can integrate and it's not a problem. But let's just say we don't know how to integrate this, right? We never learned, okay? Okay, so if we're not going to do inverse CDF, what we're going to do is we're going to do rejection sampling. Okay, and basically we have a proposal distribution, g of x. This is our proposal, or what else do we call this thing? Candidate distribution, okay? Proposal or candidate distribution. And in our case, g of x will be, is the uniform distribution from 0 to pi over 2. Okay. So this means, so this is what we want, and this is what we will propose. G of x will propose from 0 to pi over 2 evenly, okay? So all values between 0 and pi over 2. So how can we get this, okay, and this is supposed to be smooth, out of this, which is a rectangle? So under our proposal distribution, all values between 0 and pi over 2 are equally likely, but we don't want that. We want values around pi over 4 to be more likely, and values around 0 to be unlikely, and values around pi half to be unlikely as well. So what we do is we multiply g of x by a constant m so that m times g of x is greater than or equal to f of x for all x. Okay, and so now our picture (0 to pi over 2) will look like this. Okay, this is supposed to touch. It doesn't have to, but this is basically g of x times m, okay? M times g of x is our purple line, and so this value is always greater than or equal to the PDF f of x, okay? Is that okay? And basically, it's kind of like we are going to just throw a random dart inside the purple box, okay? So we will propose, what do we call this? We propose x coming from uniform, coming from g of x, okay? So in our case, we'll propose a random value from uniform 0 to pi over 2, as defined by this, okay? So some value is going to be proposed. So maybe I will propose a value right here. So maybe I propose this value. So this, I propose this value. I don't know what that is, okay? A small value, right? So then I'm going to basically look at just like this tiny little slice here. Okay. And when I look at this tiny little slice of these values here, we see that not all of these values should be accepted, okay? And so let's say this is, I don't know, at 30% or something, okay? We will accept this value with probability 0.3 or something like that, okay? And so I propose this value, and then we will accept x with probability equal to f of x divided by m times g of x. So in our case, this is just the the ratio between the height of our bar and the height of the purple line, okay? So this is the ratio between f of x and the candidate distribution. Okay, so the way you do that is you generate u from 0 to 1. And then we will accept x if u is less than or equal to f of x divided by m times g of x. Okay. So you're basically going to just randomly pick a point between here and here according to the uniform distribution. So all of these values are equally likely. If you pick a value like right here, and then you propose a value, basically from 0 to 1, this is, and if that value ends up right here, then wherever it's below the curve, you will accept it, okay? Whereas if you propose a value out here, you will generate a value and it will get rejected quite often because you have to propose a value between 0 and 1, and you will only accept it only if that value is below the curve there. Okay, we'll have to cover this some more on Monday. Okay, and we'll see how far we get. But I think we can do it. Okay, so this is the beginning of rejection sampling. Okay, you can it's also covered in the textbook, and we'll see it some more there. Okay, all right, have a great weekend, you guys, and we'll see you guys on Monday.